All right, let's talk about a word that can make even the biggest math fans get a little bit nervous: logarithm. But I'm going to promise you, by the end of this, you'll see it's not scary at all. In fact, it's a really cool tool for asking a question just in reverse. You ready to see what I mean? Let's go. So, you see something like this on a test, right? And your brain might just switch in a panic mode. I mean, it looks complicated, with all these little letters and numbers tucked into different places. But what if I told you that's not an instruction? It's just a question written in the secret language of math. Think about it like this. Exponents are like baking a cake. You've got the recipe, in this case 2 to the power of 3, and you just follow the steps to get your awesome result, the number 8. Now, a logarithm is the total opposite. It's like you're a detective. You found the finished cake, this 8, and you know the main ingredient was 2. Your entire job is to figure out the original recipe. How many times did we have to multiply that 2 to get here? And that, right there, is the absolute heart of it. Logarithms are simply the reverse, the inverse of exponents. They ask the question that an exponent answers. They really are just two sides of the exact same coin. Look here. On the left, you have the action. 2 times itself 3 times gives you 8. That's the exponent doing its thing. But on the right, you've got the question that the logarithm is asking. Okay, I started with a 2, and I ended up with an 8. How did I get here? What power did I need? See? They're perfectly connected. One is a statement, and the other is just a question about that very same statement. So let's learn the lingo. In log base 2 of 8 equals 3, that small number down at the bottom, our foundation, that's called the base. That's the number we're starting with, R2. The number we're trying to get to is just called, well, the number, in this case 8. And the answer, the key that unlocks the whole puzzle, is 3, which is the exponent we were looking for all along. The base, raised to the exponent, gets you the number. Simple as that. Okay, you've got the theory. Now it's time to actually put it into practice. Let's think of this as level 1 of a video game. Time to get some points on the board. And here's our first challenge, log base 10 of 100. Now remember, don't try to solve it right away, just ask the question, what is this really asking us? It's asking 10 raised to what power gives us 100. Just think about it for a second. And there it is. You already know that 10 times 10 is 100. In exponent language, that's just 10 squared. So the missing power, the answer to our question, is 2. See? Not so bad, right? Level 1, complete. Okay, you totally crushed the first level. So let's ramp up the difficulty just a tiny bit. This next one might look a little weird, but I promise the logic is exactly the same. It's time to level up. All right, our next challenge, log base 5 of 0.2. Now, that decimal makes it feel different, I know, but don't let it throw you off. We start by asking the exact same question. 5 to what power gives me 0.2? So the trick here is to make the numbers speak the same language. Let's change that decimal, 0.2, into a fraction. Well, that's just 1/5. Ah, now look at the question. 5 to what power equals 1 over 5? This is where you gotta remember those exponent rules. A negative exponent flips a number into a fraction. So 5 to the power of -1 gives us 1/5. The answer is -1. And just like that, you see logs aren't just for huge numbers. They work perfectly with fractions and decimals. Level 2, complete. You've cleared the basics. You've handled negative exponents. You are so ready for this. It is time for the final boss of our little explainer. This is where logarithms stop being just a question and become a seriously powerful tool for solving tricky equations. Okay, here's the situation. 3 to the power of x plus 1 equals 20. And we've got a problem. 20 isn't a nice, clean power of 3. 3 squared is 9, 3 cubed is 27. We've completely overshot it. So how in the world do we solve for x when it's stuck way up there in the exponent? We need a tool that can bring it down to our level. All right, here's the game plan. Step 1, we're going to apply a logarithm to both sides of the equation. We can do that because, in algebra, what you do to one side, you have to do to the other to keep things balanced. Step 2, here comes the magic. Logs have this superpower called the power rule. It lets us take whatever is in the exponent, in this case that whole x plus 1 chunk, and just bring it right down to the front to multiply. Look at that! Our x is no longer trapped up there. Step 3 is just good old algebra. To get x plus 1 by itself, we divide both sides by the log of 3. And steps 4 and 5? Well, now we just need a calculator to get the values for log of 20 and log of 3, do the division, and subtract 1 to finally solve for x. And after we punch in those numbers, boom, x is approximately 1.727. We actually did it. We used a logarithm as a tool to solve an equation that would have been pretty much impossible otherwise. Final boss defeated. So seriously, congratulations. You've faced down exponents, you've handled negatives, and you even took on algebraic unknowns. You've pretty much unlocked a new superpower in math. But what is it actually good for? Outside of a math test. Let's do a super quick recap with a little cheat sheet. First, and this is the most important thing, log base b of a equals c is just a different way of saying b to the c equals a. They are the exact same idea. Also, a pro tip, if you ever see log just written by itself without a little base number, you can pretty much always assume it's base 10. We call that the common log. And if you see ln, that's a natural log. It's a special type that uses a famous number called e as its base, and you will see it everywhere in science and finance. And this is why it all matters. Logarithms are literally everywhere, especially when we need to measure things that have a massive range of values. The Richter scale for earthquakes, it's logarithmic. That's why a magnitude 6 quake is 10 times more powerful than a 5. Decibels for sound, also logarithmic. It's why a rock concert is thousands of times louder than a whisper. Anytime you're looking at huge exponential growth or intensity, from your savings account to bacteria in a lab, logarithms are the tool we use to make those giant numbers make sense. So, you see, in the end, a logarithm isn't really an answer. It's a way of asking a question about growth, about intensity, about how long does it take to get from here to there. It's a tool for looking at the world in a totally new way. And now you have that tool. The only thing left to decide is, what questions are you going to ask with it?